Hi, my name is Drew Tiagi, and in this video, I'll be going over how space elevators could theoretically work. So to start, why are we researching how space elevators could theoretically work? Well, to start, space elevators would be a great way to be a safer, easier, and cheaper way of transporting small payloads to space. So currently, if we want to transport payloads like astronauts or materials to places like the International Space Station or satellites in space, we have to use rockets. And so the issue with rockets are they're expensive, right? To transport even about like a pound of material, it'll cost you about, thousands or even more in some cases. So thousands per pound for a rocket. Theoretically, a space elevator could solve this issue because it would be much cheaper, much easier, because you wouldn't need to send a whole rocket to transport these materials, and it could be safer because rockets can also, often be dangerous. And so theoretically, space elevators, some estimate, could be 95% cheaper at transporting materials, and they could really cost, in the dollars per pound versus, thousands of dollars per pound. And this technology is actually being researched in some countries, like China and Japan, are planning. China, sorry, and Japan are planning on making their rockets, or sorry, making their space elevators fully functional and fully built by 2050. And while this might seem like a really outlandish goal, in part because it kind of is, this technology is improving in the materials, and over limitations we're overcoming slowly every day. So to start, let me just explain the physics behind it, and then I'll explain some limitations and why, space elevators don't exist at the moment. So to start, the physics behind space elevators, so let's imagine you're on a merry-go-round, like so, okay? And you're sitting here, and you have a piece of rope in your hand, and the rope has a piece of weight at the end. So when you're stationary, the rope's going to be, there's no tension in the rope. It's just going to be, swiggly like that on the ground. But as soon as this merry-go-round starts spinning, what you experience is a centripetal force. This mass is going to experience a force, and this force, what it does, a centripetal force, it makes the string taut. So it makes it, have tension, and it becomes, perpendicular and extended out, perpendicular to the merry-go-round. So the idea is similar to how the string becomes under tension once it's spinning. If we consider the Earth here, and we consider a string, or a really strong tether, I guess, and a counterweight, if we were somehow able to create this counterweight in such a way such that the center of mass is at this place where the force of gravity equals the centripetal force, then what would happen is that this, string would remain taut and would remain in tension, and this whole structure would be standing. Or not standing, it would more be like, it wouldn't break, this idea. Because again, the Earth is rotating, so the Earth is rotating, and the structure is rotating too. There's tension in the string, therefore it won't collapse like that. And so the idea with a space elevator is that we want the system, so we want the center of the mass of the system, so center of mass, to be at the point of geostationary orbit, so GEO. And so geostationary orbit is the exact orbit where the rotation of the Earth, so the period of the Earth, is equal to the period of the satellite, or the whatever in space. And so the idea at geostationary orbit is that, one Earth day, one rotation of the Earth, is equal to one rotation of the satellite, which means that relative to the Earth, this satellite is stationary because they're both rotating at the same speed and same period. Not same speed, the same period. Okay. So we want our center mass, which is where all the forces can be, considered to be acted upon. So we want all our forces to be acted at the center of mass. We want center mass to be at geostationary orbit because we want it to be, again, just like stationary above the Earth. And the reason why we want it stationary above the Earth is you can imagine if we had a ball and we had it not at geostationary orbit, if it was faster, it would be like a tetherball, right? It would just like rotate around the Earth, and eventually it would just keep rotating and it would become, unwrapped around the Earth. Or on the other hand, if it wasn't like this, it was going backwards, then it would just break, and it wouldn't be good. So we want it to be right above the Earth. And we do that by placing it at center mass at geostationary orbit. And so at geostationary orbit, the forces we can imagine on the system at the center of mass is the force of gravity and the centripetal force. So the force of gravity by universal gravitation is equal to G times the mass of Earth times the mass of the system over the radius squared. It's equal to the centripetal force, which is equal to the mass of the system times velocity squared over radius. Now velocity is equal to, let's see. Velocity is equal to the angular velocity times the radius. And so if we plug that in here, we get that G times mass of Earth times mass of the system over radius squared is equal to the mass of the system times the angular velocity squared times radius squared over r. So this becomes 1, this becomes r. And so what we can do is we can manipulate it. So ms cancels out. And so we're left with radius cubed is equal to G times me over angular velocity squared. Now angular velocity, that's just equal to 2 pi r over t, 2 pi over t. And so the t is the period of the Earth, one rotation, which is 1 day, or 86,400 seconds. So 2 pi divided by that. And then we know universal gravitational constant, 6.67 times 10 to the negative 11, and we know the mass of the Earth. And if we calculate this all out, we'll get an answer of 42,200 kilometers. And this is the radius from the center of the Earth. And so if we take into account that the radius of the Earth is about 6,370 kilometers, then to be in geostationary orbit, our center of mass has to be at 42,200 minus 6,370, or about 35,800 kilometers from Earth. So if our center mass is at this point, then when the system is going around Earth, it won't, fall over. So that's the point where we need to be. We need the center mass to be at 35,800 kilometers. But the issue is when we put a cable down, right? The cable has a center of mass here, right? So the center of mass of the whole system is going to go down here. And so to overcome this limitation, because by adding the cable, which has weight, obviously, the center mass goes down, we have to overcome that by using a counterweight to, put the center mass back here. And so the idea is if we just use a little bit more material, right, and we put a counterweight that's really heavy here, that adds another piece to our center mass, and we're trying to shift the center mass back to geostationary orbit. And so we can do that here. It'll shift back to geostationary orbit, and then our system won't collapse because, again, all forces you can consider in physics act on the center of mass. And so just formula-wise, how this works is the center mass is equal to the sum of the masses times their distances. And so center mass is equal to the radius from here to the mass of the counterweight, call this mcw, so radius here, plus the radius of the center mass of the cable. If it's a uniform cable, since our cable is not going to be uniform most likely, we can consider it to be uniform in this case, but usually it won't be uniform. Of a uniform cable, the center mass of the cable, the radius, that's where we consider if we have a cable. And so the mass of the cable divided by the mass counterweight plus the mass of the cable. So again, the reason why we add this counterweight is because we want to make the center mass here, and since we add the cable here, which has a mass, we have to balance it out with a counterweight, which will shift the center mass back to the geostationary center. Okay, so why will this not work? Why does this not exist? I mean, the physics, it should work theoretically, but why, isn't it out there right now? So there are a lot of reasons why, First of all, people are afraid of, construction accidents, but that's not even the main reason. The main reason why is because this cable here, has to have, an incredible amount of tensile strength, but it also has to be light and flexible because, this cable, it's going through a lot of tension. This is 35,000 kilometers long, or even more, because we need to have the cable to extend out past geostationary orbit to the counterweight. So this cable is like immensely long, and so this cable has to be really strong, to overcome, the force of gravity, the force of centripetal force here. And so the place where it has the most tensile strength, where it needs the most strength, is here at geostationary orbit, because you have the force of gravity going this way, and you have the force centripetal this way too. And so these forces here, they provide a lot of tension on the string or whatever. And so we need to have the cable be really strong in order to survive these incredibly large forces. And so currently we have a couple of solutions to overcome this issue of the tensile strength. We do have solutions like carbon nanotubes or diamond nanothreads, which promise a very flexible but also strong material that could be used in a system like this. But the issue is with these technologies, carbon nanotubes and diamond nanothreads, these are all really theoretical technologies. I mean, we've made a couple of like really tiny materials out of them. We made a couple of little strands, but the issue is we're nowhere near having 35,000 kilometers of this material. We can only get a little bit chunks. But theoretically, if we were able to get carbon nanotubes and diamond nanothreads, this technology would definitely be possible. We could definitely do it. But again, still being in the works, this technology here. Also, another issue is how this elevator will work is you'd have a little climber here. So you'd have a little robot that climbs up this rope, and that would be the elevator part. But the issue is, how would you actually power this robot? So climber, power. And so you might be thinking, why don't we just use the cable as like a long extension cord? And the reason why it's not possible is because it's 35,000 kilometers, and so you really can't run an extension cord like that long without sacrificing power, and it just really wouldn't work at that point. So instead, what about solar panel? Would solar panel work? So solar panel would in fact not work. If we've had solar panels on the top of the climber, it would have enough energy at a certain point, theoretically, but it just wouldn't be entirely feasible because it wouldn't be enough energy. Even though it might seem theoretically possible, it just wouldn't be enough energy. And so the solution right now that people are considering are using beams or lasers of power from the ground to the satellite. So the idea is, from the base station, you have your elevator, you have your climber, you would send lasers of energy to the climber to receive. The issue with this, though, is if we imagine the atmosphere, so we imagine the base, imagine the atmosphere here, if we send a beam, the energy that we get is going to be weaker when we get to the climber because the atmosphere distorts it. It reduces the energy. And so there are solutions to this too, though. The solution we have right now is we have this technology called atmospheric distortion. And basically, by using this technique, we can, use computer models and change the wave or the laser in such a way that it's able to overcome this atmospheric distortion and give, a lot of energy to the climber. And that's, most of the issues that we face right now. There's also another issue. The other issue is there's a lot of space debris in space. Old satellites, actual satellites, stuff like that. And so the issue is, if one of these satellites, this material is going to be really thin. Like, this has to be a thin material, otherwise it's going to be way too heavy. And so this thin material is really probably going to be kind of weak. So if there's a huge satellite going at, thousands of kilometers per second, and it hits this cable, it could tear it, and that would cause like a huge accident and it would collapse. And so the idea is, instead of placing it on land, the base station, we would place it on a kind of oil rigs-like structure on the water. So it'd be on the water, like so. And then, since it's on the water, we'd be able to move it, the entire structure, to dodge these space debris. So we would be keeping track of all the space debris on Earth, and we'd move this oil rig-like structure to be able to move the cable so it wouldn't hit the space debris. And one more thing, the cable, to increase the tension, you guys know, you can just make the cable wider, right? And so the reason why we can't use technologies like steel or even Kevlar, which are really strong, is because even if we make the cable like really thin at the bottom, because again, it doesn't have to be really thin at the bottom, it has to be really thick here because that's when the most forces are being applied to the cable. And so even if we made it really thin at the top, it would have to become really, 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 really wide at the top to endure all that force. Luckily, carbon nanotubes and these diamond nanothreads promise a way to make it, less of a taper and more feasible. But again, these technologies are still theoretical and people are still researching them. And yeah, those are how space elevators could theoretically work and some limitations that we currently face. If you enjoyed this video, please be sure to subscribe and leave a comment below on your thoughts. Thank you all for watching, and I'll see you guys all tomorrow. Bye.